fixed bed adsorption devices packed with adsorbents such as metal organic frameworks or zeolites operate in a transient manner. The bulk gas phase concentrations within the fixed bed vary with the distance z along the bed and with time t. At any z and t, the adsorbate molar loadings within the particle varies along with the radius. At any z and position and time t, the molar loading at the position r equals rc, the external surface of the spherical particle, is in thermodynamic equilibrium with the bulk gas phase mixture. This equilibrium is usually determined by use of the ideal adsorbed solution theory. The intraparticle diffusion is commonly described by Fick's law or the Maxwell-Stefan formulation that is really necessary for use in kinetic separations. The description of the uptake of the components within the particle forms a small part of the computational load to determine the transient development of concentrations profile within the fixed bed and the determination of the breakthroughs that are important to describe mixture separations, and such breakthroughs are of vital importance in the design of fixed bed adsorbers. In view of the numerical complexity of transient breakthrough simulations, for a description of the transient breakthrough simulation methodology, I refer you to my paper published in 2020 in ACS Omega. Watch also my video on transient breakthrough simulations on my YouTube channel. In view of the complexity of the breakthrough simulation, it is helpful to have a simplified model to describe transient uptake within the particle. And that is where we focus our attention in this presentation. When a spherical particle of radius r sub c is exposed to a bulk fluid mixture whose composition is maintained constant, the constituents in the fluid mixture will diffuse inside the particle. The LDF model is a simplified linearized description of transient uptake of the components within the particle. The LDF model assumes that Fick's law of diffusion holds, and each of the components in the mixture diffuses independent of the partner guest molecules. The LDF model was developed by the German scientist Glueckauf. Glueckauf migrated later to England, and the classic paper describing the LDF model was published in the Transactions of the Faraday Society in 1955. The LDF model applies not only to spherical particles of solids, but it can be applied to vapor bubbles on distillation trays, liquid drops on a sieve tray in liquid-liquid extraction processes, ion exchange particles, and it is also applicable to microporous zeolites and metal organic frameworks for description of mixture separations in fixed bed adsorbers. Indeed, the focus of my presentation today is on application of the LDF model to describe mixture separations in fixed bed adsorbers. I also refer you to my own paper on the applicability of the LDF model for fixed bed adsorption separations, and this paper was published in Separations and Purification Technology in 2018. To begin with, let us examine the uptake of ethane into LTA4A zeolite. LTA4A is zeolite consists of cages of 743 cubic angstrom volume. Each cage is separated from adjacent cages by narrow windows with an opening of 4 angstrom. The experimental data on component uptake of ethane is shown by the red circles. This is for the adsorption phase, where the y-axis represents the fractional approach to equilibrium. The x-axis is the square root of the time. After equilibration, the adsorbed ethane is desorbed by exposing the external surface to vacuum, and we have the desorption curve. The experimental data are from Garg and Ruthven, published in Chemical Engineering Science in 1972. Let us set ourselves the task of modeling the transient adsorption and desorption cycles. We develop a model to describe transient uptake of ethane in 4A zeolite. The transient uptake is described by this partial differential equation, where Qi RT represents the molar loading of component I, which is ethane, at position R and time t. Ni is the molar flux of ethane, and the molar flux of ethane is described by Fick's law as being a diffusivity times the gradient in the molar loading. Rho is the mass density of the crystal framework. If the Fick diffusivity is considered to be constant and independent of loading, the partial differential equation may be solved analytically. The analytic solution was first derived by R.L. Geddes, who was a pioneer in distillation technology. The motivation of R.L. Geddes to develop the analytic solution was to apply it to describe diffusion inside spherical vapor bubbles on distillation trays, and the Geddes model is widely used to calculate the Murphy point efficiencies in distillation columns. In the context of transient uptake within 4A zeolite, the analytic expression is provided here, where the left-hand side we have a numerator, which is a difference in the molar loading that is in equilibrium with the bulk gas phase mixture minus the spatially averaged loading at any time t. The denominator is the equilibrium loading minus the initial loading within the spherical crystallite. The right hand side is an infinite series with a parameter that is described by di divided by the square of the radius of the crystal. The experimental data for transient uptake in the adsorption cycle is very well described by this analytic solution, taking this value di divided by RC squared as 1.1 times 10 minus 3 with the units of seconds to the minus 1. The desorption phase, the experimental data, is modeled with the parameter di divided by RC squared equal to 6 times 10 to the minus 4 per second. We note that the desorption cycle is slower than the adsorption cycle, and the reasons for this asymmetry in the adsorption and desorption cycles is due to the thermodynamic corrections that come into play. And for further details, I refer you to this video presentation, Unary Diffusivities in Microporous. The right-hand side requires at least about 20 to 30 terms to get an accurate representation of the spatially averaged loadings within the particle. And the motivation of the development of the LDF is to reduce the computational time that is required in such calculations requiring a large number of terms. In the LDF approximation for transient uptake within particles developed by Glueckauf in his 1955 classic paper, the transient development of the spatially averaged loading at time t is written as a linear function of the driving force for transport that is considered to be the difference between the equilibrium loading and the spatially averaged loading. The constant of proportionality is this term here, 15 times the Fick diffusivity of the component divided by the square of the radius of the crystal. We have a simple solution, analytic solution to this linearized equation, and that is written in this form, where we have the numerator as Qi equilibrium loading minus the spatially averaged loading divided by the denominator term, which is the equilibrium loading minus the spatially averaged loading at time t equals 0, which is the initial loading within the crystal. An important point to note is that the LDF model applies when each component diffuses independent of its partner. Now, this assumption comes into question for kinetic separations, as I will discuss in the following slide. The Glueckauf LDF model is based on the Fick law of diffusion, and each component in the mixture is assumed to diffuse independent of its partners. The approach to equilibrium is monotonic in character. We examine here experimental data for uptake of CO2 ethane mixtures in DDR zeolite for 3 different bulk gas mixtures. In first case, we have 20 kilopascal each for CO2 and ethane in the bulk gas mixture. Here we have 40 kilopascals of CO2 in the bulk gas mixture and 20 kilopascal of ethane in the bulk gas mixture. Here we have 60 kilopascal and 20 kilopascal for CO2 and ethane in the bulk gas phase. In all 3 cases, ethane is seen to approach its equilibrium in a monotonic manner. However, the more mobile component CO2 that has a poorer adsorption strength in comparison with C2H6 shows an overshoot in its spatially average loading in all 3 cases. This overshoot is quite prominent and reproducible. The Glueckauf model anticipates a monotonic approach to equilibrium for both components because it assumes each component diffuses independently of its partners in the mixture. In order to cater for these transient overshoots that are of importance in kinetic separations, we need to modify the Geddes model by use of the Maxwell-Stefan formulation instead of the Fickian formulation. In my paper published in Separation and Purification Technology in 2018, as cited here, shows how the Geddes model can be adapted to handle kinetic separations.